All right, let's start everybody's favorite topic in algebra, and that's factoring. Now, I'm going to go over a number of topics of factoring, but I'm not going to go into each one individually for a great deal of time working many examples. If you feel like you need that type of review, there are other videos out there, instructional videos that you can find on YouTube that will go into more detail. And what I'm going to do is just kind of highlight, because this is a review chapter. Factoring is basically decomposing, for lack of a better word, decomposing a polynomial into a product of factors. Instead of multiplying binomials or binomials and trinomials and monomials times polynomials, we're going to kind of reverse the process. And the very first thing that we're going to look at is the greatest common factor. And I always tell my students that the greatest common factor is kind of like doing the distributive property reversed, in that instead of multiplying through, you're dividing out a common factor, the greatest common factor, in fact. Now, it's always the first thing you should check for when you're asked to factor a polynomial, is always look for, always look for the greatest common factor. Now, if the greatest common factor is 1, then you don't have to worry about trying to do a step factoring out 1. That's not going to help. But in the example that I have right here, my greatest common factor, I look at 8x to the third as 2 times 2 times 2 times x times x times x. I look at 12x to the second as 2 times 2 times 3 times x, and I look at 4x as 2 times 2 times x. And I look to see which factors they have in common. Well, they all have 2 factors of 2, and they have 1 factor of x. So 2 times 2 times x, or 4x, is my greatest common factor. And so I'm going to reverse the distributive property. I'm going to divide it out of all 3 terms. So I have 4x times, and then I'm going to go ahead and put the parentheses out because I have 3 terms. I've got to divide it out of all 3 terms. Now, if it helps you, what you can do is you can divide each term one at a time by the GCF. So 4 goes in that once, 4 goes in that twice, 1 factor of x here with 1 factor of x leaves 2. That gives me 2x squared. Now, I've gotten to the point that I've done this enough times that I don't have to write it out, and you probably are in that situation as well. So my suggestion would be, go ahead, divide it out like this if you can't keep track of everything. Otherwise, just traditionally, just go ahead, and I'm going to factor out a 4x out of 12x to the second. That will leave plus a 3x. I'm going to divide 4x out of 4x, and then leave 0. That leaves 1. If you divide 4x by 4x, and with that minus sign, that's a minus 1. Now, you can check your work by distributing and seeing if you don't get right back to where you started. In fact, on factoring problems, you can multiply your factors to see if you get back to the original polynomial, and that's a good check. Now, here's an example, GCF. Notice the negative sign out in front. So what I'm going to look for here for my GCF is I'm going to look for a negative, because I don't like a negative in my first term. I can see they're all divisible by 2. 2 is the largest number that divides into all of them. These 2 have x's, this one doesn't, so negative 2 is going to be my GCF. I have to be very careful with my signs here, because again, when you're dividing, you're factoring out that negative 2, you're dividing it out of every term. Negative 6 divided by negative 2 is a positive 3x squared. Minus 8x, like a negative 8x divided by negative 2 is a plus 4x. Positive 10 divided by negative 2 is a minus 5. And that's as far as I'm taking that out, factoring out the GCF. Always the first thing you should check for. Now, using the GCF idea is factoring by grouping. Factoring by grouping typically is for polynomials that have 4 terms. As the example is here, I have 4 terms. Okay, so what I'm going to do here is I'm going to factor out the greatest common factor looking at groupings of 2. I'm going to look at the first 2 terms and the last 2 terms. Now, this might not be the one that works, and I'll explain what works. You might have to group the first and the third, and the second and the fourth, and maybe the first and the fourth, and the middle 2. But it seems like about 95% of the time it's the first 2 and the last 2. So to factor by grouping is I take the GCF out in each one of the groupings of 2 terms. So the greatest common factor with 7cd and c to the second, the only thing they have in common is one factor of c. So if I factor that out, if I divide c out of 7cd, I get 7d minus, if I divide c out of c squared, it leaves a c. Over here, I have two terms. My GCF appears to be a positive 2. Now notice there, positive, negative, positive, negative. If this was negative, positive, or minus, plus, I would factor out a negative 2. But in this case, I can factor out a positive 2, that's my GCF. 2 out of 14d leaves 7d minus 2 out of 2c leaves c. And hopefully you can tell why I'm doing this, because now I have a greatest common factor of this binomial, 7d minus c. 7d minus c gets factored out of both, that leaves c here, plus, if I factor the 7d minus c out of this, that leaves the 2. If I was to do FOIL on this, I should get back to here. I might not have the terms in the exact order, but I should get right back to where I started. So that's a good check. Most of the factoring that we do are not four-term polynomials, but typically they're going to be binomials and trinomials. So let's talk about trinomials first. Now this is kind of a generic way of writing trinomials that have a lead coefficient of 1. B and C represent real numbers. We are going to kind of reverse the FOIL process to do this. Now you can do this by looking for two things here. You've got to figure out the combination of factors that will give you the b and the c here. Now, I look down here at this example, I have a y squared. If I'm reversing the FOIL process, I'm going to go to get the y squared, y and y. But how do I get the 9 and the 14 to match up? Well, the two numbers that go here have to multiply the L in FOIL to give us this. So this has to be the product of the two terms. And then when I do the outer and the inner and combine by adding the like terms, because they will be like terms, this has to be the sum. So I'm looking for two numbers whose product is 14, whose sum is negative 9. Now what gives me 14? Positive 14. Well, it could be 14 and 1 or negative 14 and negative 1. When I multiply those, I get positive 14. It could be 7 and 2 or negative 7 and negative 2. When I multiply those, I get the product of 14 as well. So what I'm doing here is I'm going to look to see which of these combinations add up to the negative 9. Well, that's the last one. I have a negative 7 and a negative 2. I'm going to write minus 7 here. I'm going to write minus 2 here. Let's do a quick check. Y squared minus 2y minus 7y is minus 9y squared. The L in FOIL gives me the plus 14. And as long as my coefficient is 1 here, this is a nice little method to use. Now when the coefficient isn't a 1 here, as I have in this example, this kind of a generic way of writing it out, a is not equal to 1, then I'm going to factor it using a different method. Now there's all sorts of methods. I was taught how to factor it by trial and error. Not always the best way, but once you get used to it, it's pretty fast. There's the diamond method, there's the factoring by grouping by breaking the middle term up, but the one that I've been showing my students is called the bottoms up method. And the bottoms up method is where I have trinomial, descending order, lead coefficients not 1. I want to make this a 1, so I take this away and I multiply it times that term over there. So that gives me x squared minus 10x minus 24. Then I use this method, because now it has a coefficient of 1. These are not the same polynomials, but it's getting me there. This is the work that's required. So I'm going to break this down with an x and an x. And I'm going to look for two numbers whose product is negative 24 and whose sum is negative 10. And I'm thinking negative 12 and positive 2. After you do a few of these, you can get pretty fast at it. So I'm going to write a minus 12 and a plus 2. Now this will not give you that if you multiply back, because I multiplied by this 3 to start the problem out. To undo that, I'm going to take each one of these constants and I'm going to divide it by that number, by 3. Now 12 divided by 3, that comes out to be x minus 4. 12 divided by 3 is 4. But this one doesn't come out evenly. 2/3 is a fraction. It does not reduce. So here's where it gets its name. I bring this from the bottom, this 3 from the bottom, I bring it up in front of the variable. So that's going to be 3x plus 2. And that is what it equals. Now again, I can do FOIL here and check my answer. I already knew that my GCF was 1 here, so I wasn't so worried about factoring out a GCF. I'm going to have to here. But I noticed that my lead coefficient was not 1, and I used the bottoms up method. All right, now in this example, my lead coefficient is certainly not 1, plus I've got an extra variable tossed in, and I have a greatest common factor different than 1. So the first thing I'm going to look for here is the greatest common factor of, looks like it's going to be 10m. I'm going to factor out a 10m out of these 3 terms here. Now that's, again, that's just dividing it out, so that's going to be 3m to the second minus 20mn minus 7n squared. I took out a GCF of 10m. Now to break this one down, notice it's a trinomial. Lead coefficient is not a 1. I'm going to use that bottoms up method. So for right now, I'm just going to do some work down here. I'm going to write this 3m squared minus 20mn minus 7n squared. Let's see if I can break this down by multiplying. It gives me m squared minus 20mn minus 21n squared, 3 times 7. Then I'm going to see if I can break this down using the method I was showing you here, an m and an m. Now I have an n squared here, so I'm going to have n's in my last terms, but I'm going to look for 2 numbers whose product is negative 21, whose sum is negative 20. And I'm thinking negative 21 and 1. You multiply, you get negative 21, you add them, you get negative 20. So minus 21n plus positive 1n or just plus n. I'm not done. Remember, if you multiply through, in this case it was a 3 as well, it's not always a 3, you have to divide through. So each one of these gets divided by 3. And again, if it helps, you put the 1 there. So 21 divided by 3, that's kind of nice. That comes out to be 7, so minus 7n. But over here, this does not reduce, this does not divide nicely, so I'm going to do the bottoms up, bring the 3 out in front. The 3 goes in front of the m, plus the 1n or n, and that is what this factors into. So don't forget your GCF, and this is going to be m minus 7n and 3m plus n. Lots of practice to get good at factoring. Now we look at some factoring that involves some of the special products that we talked about before. Special products as in squaring binomials. Notice here, a plus b quantity squared, first term squared, same sign, double the product, always, always, always a plus sign, last term squared. Same thing down here, first term squared, same sign, double the product, always, always, always a plus sign here, last term squared. So we are going to reverse that process if we can and factor trinomials that are perfect square trinomials into binomial squared. This is a perfect square trinomial. You look at it and you say, no, I just probably use the bottoms up method on this. And you could. The GCF is 1. It has a lead coefficient that's not equal to 1. You could use the bottoms up. But if you recognize this as a perfect square trinomial, and you have to look for 4 things. Is this a perfect square, the first term? Yes, it's 8y times 8y. Is the last term a perfect square? Yeah, it's 1 times 1. Is this a plus sign right here? Absolutely it is. Because you have to have that positive, you always, always, always a plus. And then the tricky one. Is the middle term, ignore the sign for right now, is the middle term double the product? Well, the product of the 2 things that are being squared in the first and last terms, that's why I wrote them down, the 8y and the 1. If I take the product of those and double it, I get 16y. If all 4 things turn out to be true, then this thing will factor into a binomial squared. First term, what's being squared in the first term? Last term, what's being squared in the last term of the trinomial? The sign that goes between them is the sign in front of the middle term. If this is plus, then this is plus. If this is a minus, then that's a minus. I say that sign for the end. If you square that out, you should get right back to where you started. Here's another example. trinomial, descending order, with respect to m anyway. Lead coefficient is not a 1. You might be thinking bottoms up, but again, let's check the 4 things to see if this is a perfect square trinomial. This is 3m squared times 3m squared, perfect square. This is 5n times 5n, perfect square. This is a plus sign. So now the tricky one, does this result from taking the product of what's being squared in the first and last terms and doubling it? If I multiply 3m squared times 5n, I get 15m squared n, double it, 30m squared n. It works. So this is going to equal the square of a binomial. The first term is 3m squared. The last term is 5n. And again, the sign that goes in front of the middle term is the sign that goes in the binomial that's being squared. So if you can remember these, a lot of students struggle with this, but if you can remember these can be a time saver. Another special product that we had before was the conjugates. When we multiplied the conjugates, the O and the I dropped out, and we got this expression, which is a difference, minus difference, of 2 squares. That's a perfect square, A times A, that's a perfect square, B times B. So if we use that in reverse, we'll see if we can factor binomials that kind of look like this. Well, the example that I have written here, the first thing that grabs my attention, and again, it's not something that everybody looks for, but the first thing that grabs my attention is that I have a GCF other than 1. 2 goes into both of these numbers. Now you kind of look at it and think, maybe something bigger than 2. I think 2 is it. So I am going to first factor out the 2. Divide the 2 out of here, divide the 2 out of here. That's going to give me 16y to the 4th minus 81. Well, there is my difference of 2 squares. Difference, that's a perfect square. That's 4y squared times 4y squared. That's a perfect square. That's 9 times 9. So this, if I reverse the process of multiplying conjugates, I am going to get, and don't forget your GCF, I'm going to get 2 conjugates. I'm going to get a 4y squared and a 4y squared. I'm going to get a 9 and a 9. And one of them is going to be a plus and one is going to be a minus. Do you put the plus here and the minus here? Doesn't matter. You can put the minus here and the plus here. It's the same effect. I'll go ahead and put the minus there. I'll put the plus here. And it looks like I am completely done factoring. I took the GCF out, and what was left factors the difference of squares. Well, occasionally it factors further. Or if you tell your dad about this, it factors further farther. This is a difference of squares right here. Now that's a sum of squares. It does not factor, but a difference of squares will factor. So I can break this down even further. 4y squared plus 9. Because that's a perfect square. That's 2y times 2y. That's a perfect square. That's 3 times 3. That's a minus sign. It's a difference of squares. So I'm going to put a 2y and a 2y. I'm going to put a 3 and a 3. And then again, it doesn't matter if you put plus, minus, or minus, plus. This time I'll go plus, minus. It doesn't matter. And that's going to be as far as that factors. That's a monomial. That's not going to factor. This is not going to factor. This is not going to factor, even though it's a binomial with a minus sign. These are not perfect squares. And this is not going to factor, as that is the sum of squares, which does not factor. 2 very special products here that involve, or 2 very special forms of factoring that gives us products of a binomial and trinomial are what we refer to as a sum of cubes and a difference of cubes. Now, I can tell you, most of my pre-calculus students that I've had over the years have a tendency to forget this. These are good ones to remember. They show up just enough to be kind of a pest as far as working the problems out. If you don't practice them every so often, you have a tendency to forget about them. But we'll do an example right now where I'm going to factor. I'm going to factor x to the 3rd plus 64. That is a sum of cubes. My GCF is 1. That's a perfect cube. X times x times x. That's a perfect cube. 4 times 4 times 4. Now look how similar these patterns are. They look exactly the same, except these 2 signs get reversed here. So remember, when it's a plus, it starts with a plus and has the minus in front of the middle term. When it's a minus, it has the minus in the binomial, has a plus in front of the middle term of the trinomial. So this is going to factor into a binomial times a trinomial. Okay, the binomial, what's being cubed here, what's being cubed here, keep the same sign. and this is how I remember it. Square the first term, opposite sign, take the product, a times b, or in this case x times 4 is 4x, always a plus, notice always a plus here, and then take the last term and square that. Now, you can tell that's not going to factor any further, but that kind of looks like that might factor using the method where we're looking for two numbers whose product is the n constant term and whose sum is the coefficient of the middle. You're not going to find them. That trinomial is not going to factor for you. All right, very similar. If I write down factor, and let's try 8y to the third minus 27. That is a difference of cubes. This is 2y times 2y times 2y. This is 3 times 3 times 3. We're going to use this method right here into a binomial times a trinomial. The binomial is 2y. 2y times 2y times 2y, and a 3 here, 3 times 3 times 3, and the same sign. Now we get this part over here, remember, from taking the first term and you square it, that's 4y squared, opposite sign, plus, then the product, 6y, then it's always a plus, and 3 times 3 is 9, and you get the quantity 2y minus 3 times the quantity 4y squared plus 6y plus 9. We'll try one more of these just to keep us honest here. Let's see if I have a good one for this. We'll do one more here. I've got one more example. 64v to the third minus 125y to the sixth. It's about the same as the last one, except that I have a little higher powers there for my variables. But this is a difference of cubes. This is 4v times 4v times 4v. This is 5y squared times 5y squared times 5y squared. Difference of cubes is going to give me a 4v and a 5y squared minus first term squared, opposite sign, take the product, that's 20vy squared, always a plus, and then the last term squared is going to be 25y to the fourth power. Okay, we've looked at individual types of factoring. Now what we're going to do is we're going to come up with a strategy when we get a problem, and we're going to look at problems that maybe even factor further, have little tricks involving negative exponents or some type of substitution that can be used. But always, always, always check for the greatest common factor first. If it's 1, then you're ready to go on. Count how many terms. 2 terms, it's probably either a difference of squares, a difference of cubes, or a sum of cubes. If it's none of those, then it just doesn't factor any further. If it has 3 terms, it might be a simple trinomial that you can factor using the little trick of finding 2 numbers whose product is c, whose sum is b. Or maybe it's in this form where we use the bottoms-up method. Or maybe we discover by checking the 4 things to look for that it might be a perfect square trinomial. If it has 4 terms, we're pretty much doing grouping. And as I mentioned with grouping, 90% of the time you group the first 2 and the last 2, although I have an example that's a little different that's coming up. Now, after you've factored using any of these methods, check to see if any of the factors factor even further. Now, monomials aren't going to factor any further, so if you have a GCF that factors out, that monomial is not going to change. But perhaps what's left after you factor out a GCF or after you break them down using any of these methods might factor even further. And of course you can always check your work by multiplying it back out. Now I have some examples here that I'm going to finish this section with, including this first one where I have 4 terms and my GCF is 1, so I'm thinking I am going to factor by using the grouping method. And I'm looking at maybe 2 and 2 here. These 2 and these 2. Now I notice it's plus, minus, minus, plus, so I have to be careful with my sign. My first 2 have a greatest common factor of x to the third, leaving x squared minus 1. My last 2 have a greatest common factor of 64, but since I am changing the signs here to match the signs here, plus, minus, I'm going to factor out a negative, or minus 64, and that will leave x squared, and that of course is going to change the sign to minus 1. These match perfect, so I take out the GCF of x squared minus 1, leaving x to the third minus 64. And what's unusual about this problem is that after you factor with grouping, each of the factors factor further. The first one is a difference of squares, the second one is a difference of cubes. So this factors into conjugates, x minus 1, x plus 1. This factors into a binomial and a trinomial. This is x times x times x, 4 times 4 times 4, so x minus 4, same sign. First term squared, opposite sign, the product, always a plus, and then the last term squared. You don't have to worry about this factoring further. So you have 4 different factors. The one to the right there is also have 4 terms. So you figure maybe grouping, the GCF is 1. But in this case, if you group the first two, they really don't have anything in common. These will have a 3n. If you try grouping these, then they have a 6 in common. But this one doesn't have anything. It's a little tricky. What I'm going to do is I'm going to group these 3 and 1, or 1 and 3 in this case. So I'm going to leave the first term alone as 36 minus, but I'm going to factor out the negative here, and that leaves m squared plus 6mn plus 9n squared. And I notice that inside these parentheses is a perfect square trinomial. This is, right here, a binomial squared. First term, m times m. Last term, 3n times 3n. Plus sign here, and double the product gives me the middle term. So an m, a 3n, and a plus sign. And it looks like I'm all done kind of in a weird way, but I really didn't factor the entire polynomial, just the last 3 terms. But I have a difference of squares here. A difference of squares. I have 6 times 6, that's an m there. I have m plus 3n times m plus 3n. So I am going to break this down into a 6 and a 6, and m plus 3n, and m plus 3n. One's a plus and one's a minus. Now I want to drop those parentheses inside the brackets to simplify this a little bit. Sometimes you might get even like terms, but in this case I get 6 plus m plus 3n. It's like a negative 1 here. So I'm going to get 6 minus m minus 3n. And that's as far as that one's going to go. Even though there are 3 terms here, we don't have the traditional quadratic effect to factor further. Now this next one, you can use a substitution here to kind of help you out, because right off the bat you might think you have to multiply all that together. But if I see that I have an expression squared, and then I have that expression to the first, and I have a constant, I don't have a quadratic, but I have something that has the look of a quadratic. Remember an excess song back in the 80s? It's got the look. This has got the look of a quadratic. So if I let u be x squared minus 2 and plug that in, I have u squared plus 5u minus 14. This is called a u substitution. The reason that we use u is so that when we say this out, we say u equals x squared minus 2. We can say u is x squared minus 2, and you don't get to say u is very often. Now this has the effect of the trinomial. This, in fact, is going to be something along like this, where I'm going to look for 2 factors of 14 that add up to 5. U, looks like I need a positive 7 and a negative 2, plus 7 minus 2. Now, we didn't start with u in the original problem. We don't want to finish with u in the original problem. We must make that substitution back out. This right here goes in for the u in both spots. So I have x squared minus 2 plus 7, x squared minus 2 minus 2. Now, x squared minus 2 plus 7 is going to give me x squared plus 5. X squared minus 2 is going to give me x squared minus 4. Son of a gun, I have a difference of squares. This factors even further. This is a fun problem. This is x squared plus 5. This is going to factor into conjugates. An x and an x, a 2 and a 2. One's a minus, one's a plus. And I go ahead and put that in, and that's my final answer. This is called u substitution. We use this a lot in calculus. For this example over here, it looks like it'd be pretty tricky to factor because of the negative exponents. But what my suggestion would be is, since I have the same variable, factor out the smaller degree here of the -5, factor that out of all three. Now if I factor that out, an a to the -5, it's as if I'm dividing again each one of these by a to the -5. So that's going to leave me 11. A to the -4 divided by a to the -5, -4 minus a -5, minus 3a. -3 minus a -5, that's positive 2, plus 2a squared. So this turns out to be a to the -5, and I'm going to rewrite this into descending order, 2a squared minus 3a plus 11. Now, you should check to see if this factors, because I have a trinomial. It looks like I would use the bottoms up method here by breaking that over, making that a 22. I don't see this one factoring any further. You can go through the steps and check, but that's as far as that's going to go. But I'm going to write my answer without the negative exponent. I'm going to write this as 2a squared minus 3a plus 11 all over a to the 5th power. Here I have a negative exponent, but I have a negative rational exponent. So I'm going to kind of use that same GCF trick with the negative exponent, and I notice that both base 4x plus 3. This might be a good one for a substitution as well. If we let u equal 4x plus 3, I would get, for right here, I don't want to substitute in there quite yet. You know, maybe I'm going to cause more trouble having the two variables. Let's see if we can do this one without the substitution. I'm going to factor out the smallest exponent, the 4x plus 3 to the -3/4. If I divide that out of this is all going to be gone, and that's going to leave an x. Plus, if I divide 4x plus 3 to the positive 1/4 by 4x plus 3 to the -3/4, 1/4 minus a -3/4 is a positive 1. So that's going to leave 4x plus 3 to the 1st power, or just 4x plus 3. I'm going to rewrite this by combining like terms, and I'm going to put this guy in the bottom, and I'm going to have 5x plus 3 all over the quantity 4x plus 3 to the positive 3/4. And I'm going to leave it like that. Now, as I mentioned when I started this, there are so many different kinds of factoring examples that you will come across. They're not always going to match exactly to one of the examples that I've done, or one of the examples in your textbook, or one of the examples in the notes. But if you practice this enough, after a while you pretty much see all the different kinds of things that can happen, and you get used to the patterns. But it does require a lot of practice, practice, practice.